This video is part 2 of Chapter 11, Describing Data, Confidence Intervals, and Correlation for PSY 222, Research Methods in the Psychological Sciences. In this part of the chapter, your authors are walking you through the logic of using confidence intervals in the third part of conducting data analysis, which is where you're confirming what your results mean. Now, I will preface this section on the statement that this part of the PowerPoint is really just walking you through an example. So me kind of talking and reading numbers off the screen isn't likely to be particularly useful for you. So what you may prefer to do instead is, rather than watching this part of the lecture and expecting to have a miraculous understanding of confidence intervals, you may want to sit down with the notes version and your textbook. And also I've included a video link to someone who's provided a more in-depth explanation of the statistical information and an additional set of examples to help you understand better. So what we're doing in this third stage of the data analysis process is confirming what we found. So confirming what the data reveal, and by confirming, we're confirming, does my sample reflect what my population is? So it's ultimately a question about that issue. One thing that is commonly done, and you may have noticed this, you may not, confidence intervals are sometimes included in the output that you look at after you've run a test using SPSS. So one approach to this is to calculate confidence intervals for a population. The interval can be calculated, and you really have to start by having an image of a normal distribution in your head. So imagine a bell curve in your head while you're thinking about these ideas. We may look at a single population mean, or we may be looking at the difference between population means, such as between groups. The confidence interval, when you're talking about a population mean, is going to be a range of values, a high and a low, and between those two values, we can conclude that if our obtained value is between those two, that the population the population mean is likely to be in that space. Now again, as we work through some examples of this, this should become more clear. There are also examples in your text, and there are examples in the video link that I provided on D2L. Typically the expectation is that we want to have confidence of 95% or 99% that this range houses the population mean. The calculation, as it's laid out for you in your text, and these formulas get pretty busy pretty fast. Try not to let them overwhelm you. They have a lot of pieces parts, but the pieces parts themselves are pretty straightforward. The confidence interval around an estimate of a population mean is something we want to do with 95% confidence. So pretty darn sure, maybe a way of putting that. The formulas, and again, this is copied straight out of your chapter. You want an upper limit to be the mean, and then the 0.05 here, that tells you the 95%, and the standard deviation of that mean. The T was with the subscript of 0.05. That's a value of a T statistic that you would look up in a table with a degrees of freedom value of n-1. So the alpha is going to be, the p-value is going to be 0.05 for the test, M is the mean of the sample, and the S sub M is the estimated standard error of the mean. I misspoke earlier. I think I said standard deviation of the mean. Apologies. So for example, let's say we had 30 students who took a test. The mean of the sample is 115 with a standard deviation of 14. You can ask the question, is this mean, this sample mean, a good estimate of the whole population? So let's say you have a group of kids at an elementary school in Stark County, and they all take this test, and they get this mean. Is that mean a good representation of the whole population of children of the same age? Because we could make that, we could ask that question, are these kids really representative, or are they different? So that's what we're really doing here with these confidence intervals. The estimated standard error of the mean is going to be calculated using the information that you have. So you're going to use the standard deviation that you have, the 14, and the sample size to calculate that estimated standard error of the mean. And then you have a critical value of t. You know what the degrees of freedom are. So the degrees of freedom are n minus 1, that's 29. And you have this, your alpha level at 0.05, the critical value is going to be 2.04. So if you're following the logic here and you want to determine what are the confidence intervals around that 115 with the value that we've just calculated. So we determine, and remember how I told you to imagine a normal distribution in your head? You have this mean of 115, and you have an upper limit of 120.2 and a lower limit of 109.8. Those are your upper and lower limits. So you can state with about 95% confidence that this range from 109.8 to 120.2 contains the population mean. Now remember how in part 1 we said you really want that standard error to be pretty small. With our confidence intervals, our preference would be that they're pretty bounded, so that you can say the narrower that interval, the more confident you are that the population mean it has been approximated with your sample. The bigger our sample, the better our ability to estimate that population mean with confidence. Now, if you're looking at the difference between two means, and when I look at a formula like that, my not gifted at math self kind of goes, I wish I had an ice pick and I could stick it in my eye right now. But really, if you look at the individual pieces of the formula, they're not complicated mathematically. Your goal is to really understand what we're doing in a broad sense, as opposed to being able to do the math of it adroitly. So when we're using confidence intervals, what we want to do is to construct these intervals for the differences for different scores. So let's say you're comparing the boys and girls in your class of 30, and you want to know how well do the differences between these two groups reflect the differences in a population of the same subgroups. So instead, you're going to substitute difference between two means in place of a single mean, which is what we did on the previous slide. And you're going to use the estimated standard error of the difference between the two means, as opposed to the standard error of just one mean when we're working through the formula. So for example, you could want your confidence interval information to be about the effect of an independent variable, where your independent variable represents two groups. Let's say it's one group has been exposed to a treatment like a reading intervention, and the other group has not. They're the control group. So you have experimental versus control. And you want a confidence interval of 95%. You have the mean of the first group minus the mean of the second group, and the standard error for that difference. Now, suppose a treatment is designed, in this example, to improve memory. The dependent variable is recall on a memory test, and you know what your two means are. So when you eyeball these, the mean number of words recalled for the treatment group is 64. The mean score for the control group that hasn't been exposed to the treatment is 45.58. Here's your standard deviation values and your sample ends. With those pieces of information, you have the necessary components for determining your confidence intervals. You also need, though, to calculate the standard error of the difference, the mean differences, and you can do so by running the formula. The critical value that you're going to use is based on a 0.05 with a DF of 50. And where does the 50 come from? You're going to use your combined N to calculate your degrees of freedom. So if you're following the example, the confidence interval that you're going to calculate will be, you'll be plugging in the values here. Your upper limit is going to be 24.81, and your lower limit is going to be 12.1. And what you can say there is that there's a 95% probability that this range from 12.11 to 24.81 includes what you would obtain as a population value, the difference between the means. So if you had access to the entire population of humans who then are exposed to your intervention and compared to a control group that's not exposed to an intervention, that the mean you got, the mean difference between the two groups would land somewhere between those two scores. So the conclusion you could draw is that mean memory performance as measured by this test can be expected to improve scores within that boundary. So you may not get the exact improvement that you see in your test, but your level of improvement can be expected to be between these two amounts of increase. Now, if we're trying to interpret these comparisons between means using confidence intervals, you do note that you can have a confidence interval with 0. When you don't include the 0 in the confidence interval is under certain circumstances. So if you're going to be more, if you're in a situation where you're more confident that the population means are different, and when an effect is likely. So if you don't see a 0 in the confidence interval, then you can be more confident that you actually have a population means difference that you can infer based on the difference in your sample. And what that suggests to you is when you don't have a 0 value in your confidence interval, it suggests that your independent variable had an effect. If 0 is included in the confidence interval, then you can't conclude with certainty that there's been an effect of the independent variable. And it's possible that the independent variable has no impact on your dependent variable scores. When you're comparing multiple groups with confidence intervals, the procedure is somewhat different. You have to compute your confidence interval for each mean for each group. And then you have to use something that's called a pooled standard deviation to estimate the error of the mean. After you've calculated the confidence intervals, if the confidence intervals don't overlap, And again, it helps if you imagine some distributions. Imagine that each of your groups has a separate distribution of scores. And what you're looking for is, if you've calculated the confidence intervals for each group, do those confidence intervals overlap? If they don't, then you can say with more confidence that the population mean that you're estimating is actually different between those two groups. If they do overlap, then it suggests that the mean differences you've observed in your samples are not likely to be seen in the population. If they overlap only a little, as opposed to a lot, that means we need to do more research, perhaps with larger N, in order to draw a more confident conclusion. If you have a sample mean that falls inside the confidence interval for another group, then what you're supposed to do is to conclude, and this could even be if you have a significant test result, you are to conclude that the populations from which the samples were pulled are actually not different from one another. Now, as I said, and this concludes part 2, be patient as you're reading the section on confidence intervals. Look at the images that you're provided in your chapter and review the extra video that I've posted for you.